Okay, in today's lesson we're going to continue talking about inverse functions. Some of the key concepts today. What does it mean for an inverse function to exist? What are the conditions under which an inverse does exist? And what does the domain of a function have to do with identifying an inverse correctly? We need to understand a little bit about relations and functions. Relation is any set of x and y values. You can always see a relation because it can be graphed on an x and y axis. A function is a little bit more specific. A function is any relation for which there is no more than one possible y value to each x value. We can easily ascertain that by using something we call the vertical line test, where we can intersect the graph with a vertical line. If it's possible to intersect the graph twice with a single line, we're looking at something that is not actually a function. So for example, in the first graph there, when I'm looking at this maybe parabola, anytime that I use a vertical line, it's only going to intersect once. So I'm going to get you to pause the video and do a quick sketch of those graphs and use a vertical line test to find out which of those relations are actually functions. Okay, so looking at some vertical lines here, we can see for many of the graphs there's only one possible intersection. So for this graph, this type of graph, there are two graphs there where a vertical line would intersect a graph twice. So we're looking at a couple of relations that cannot be defined as functions. So there we go, just to clarify, in that collection there we've got 4 functions and 2 relations that are not functions. The second question we need to ask about functions in determining whether or not they have an inverse is whether or not the functions are one-to-one. And what that means is that the function only has one x value to each y value, or no more than one. And that is simply a horizontal line test. So this is a new collection of functions. Quickly sketch these, and I'm going to give you a moment to see which of these pass the horizontal line test. There we go. So we've got a couple of functions there where a horizontal line will intersect the graph twice. What that shows us is that for that value of y, there are 2 possible values of x, or importantly, more than one. So the green ticks there, they show us functions that are one-to-one functions. The 2 crosses are showing us they are functions, but they are not one-to-one. So we've got 4 functions there for which the inverse is also a function. Just to summarise that point, so the existence of an inverse function depends on the function itself being one-to-one. And what we can see here in the illustration is a many-to-one function, something that doesn't pass the horizontal line test. When we reflect that in the diagonal line y equals x, we can see what the inverse would look like. The inverse is a relation, but according to the definition of function, it's not a function. So there are 2 questions there. Is the original function actually a function? If so, it passes the vertical test. And is that function a one-to-one function? One value of y to every value of x and vice versa. It passes the horizontal line test. So we're going to I'm going to give you a moment to have a look at this function, this question, and I want you to ask yourself, is the inverse a function? And if it is, can you state its domain and range? You can pause the video. First of all, let's see if the inverse is actually going to be a function. Does it pass the horizontal line test? Let's have a look at a horizontal line. Wherever I draw a horizontal line, there is only going to be one intersection. It's a one-to-one function, so yes, there is an inverse. Let's think about the next question. Can we state its domain and range? If you remember from the definition of an inverse, the domain of a function is going to give us the range of its inverse. So even from the way the function is written, we can see the domain there. The domain is all real numbers. The graph also shows us that the domain is all real numbers. And so this tells us that the range of the inverse is all real numbers. If we're thinking about the domain of the inverse, that's where we need to look at the range of the function. And so we go back to the graph. What does the graph show us about the range? We can see we're looking at an exponential function here with a horizontal asymptote. What's the range of that graph? Its range is -2 to infinity, not including -2. And so that is going to be the domain of our inverse. All the values, all the real values above -2. So just to summarise there, the domain of the inverse, all the values above -2. The range of the inverse is all real numbers. Let's have a look at a sketch of the inverse just to check. You can see here I've sketched a function by reflecting that function in the horizontal line, y equals x, and we've got the graph of its inverse. And we can see from that graph, because of the asymptote, its domain is from -2 to infinity, or above -2 rather, and the range of the function, all the possible y values, are all the real numbers. It might also be clear that the original function is an exponential function, and the function of the inverse, we're looking at something that's a logarithmic function. We're going to look at another graph now, same questions. I'm giving you a function, this time it's a quadratic function. I'd like you to ascertain whether or not whether its inverse is also a function. If you decide that it is, can you state its domain and range? If it's not going to be a function, we're going to think about restricting the domain so that it is. It's a good idea to start with a sketch, so I'm going to give you a moment to sketch that function and to think about those questions for a moment. There's a sketch of the quadratic function. We've got a parabolic shape that has a turning point at -2, 3. Does it pass the horizontal line test? Is it a one-to-one function? And we can quite easily see that for one value of y there, we've got two possible values of x. So we're looking at a function of x for which its inverse would not be a function. So what do we do about that, or what can we do about that? We can restrict its domain, and this is going to get a little bit technical, so feel free to pause the video if you need to read things and keep up. What I've done here is to restrict the domain. I've sort of split the function into two new functions, and I'm calling those functions f1 and f2. So I'm using the left-hand side of the parabola right down to the turning point. So the domain of function 1 is from -infinity. The upper limit is -2. In function 2, I am using the right-hand side of the parabola, so all the real numbers from -2 to infinity will be the domain of that function. And actually, both of these functions should actually have square brackets. I'm just going to pop those in. Okay, so I've fixed up those domains. We've got square brackets because it includes the value x equals -2. Now the reason for doing this is that both of those functions are now one-to-one functions. Let's have a look at the rule for the inverse. And you'll remember from finding rules in the previous video, we're going to swap x and y in the rule for the function, and we solve for y. We get that our function is going to be the plus or negative square root of x minus 3 minus 2. It's really important here that we use the positive and the negative, because as you're going to see, we've actually got different rules for each inverse. We can see which rule is applicable with each of those functions by looking at the graph. And this highlights that graphs are really important when we're thinking about functions and their inverses. So we've got the diagonal line. Let's reflect each of those functions in that diagonal line. So the inverse of the function number 1 is a square root function, but you can see we've got this reflection in the x-axis. The function's upside down. In the second function, when we reflect f2, we've now got a square root function, but it's not been a reflection in the x-axis. We've got the positive square root of x minus 3 minus 2. So we can outline the rule for the inverse and the domain for the inverse function for each of those graphs. So you might want to pause the video and have a look at this, but I'm just highlighting out a few things. Here we've got the rule for the first inverse. It's got a domain of 3 to positive infinity, and the rule for that, because it's a reflection in the x-axis, is the negative square root. The second inverse function has exactly the same domain, and the rule is the same rule apart from it's got a positive square root of x minus 3. So here you can see by restricting the domain and doing it in either way, we come up with the rules for inverses, and those rules are going to be different. Let's have a quick look at the CAS calculator and see what would happen if we tried to use the CAS calculator to find the rule for the inverse. So I'm going to start by defining the function. Our original function was f of x equals x plus 2 squared plus 3. Define that function. And remember, we can solve the inverse function by asking the calculator to swap around x and y and then solve for y. And the calculator also outputs two different rules for the solution for y. So y, as we can see there, y can be a negative square root function reflected in the x-axis, or it can be a positive square root function. So one thing I want to highlight in this video is in all questions or problems when we're dealing with functions and their inverses, it's really useful to be able to either look at a graph or to sketch a graph. This is one reason why sketching skills are really important, that you develop those. The second thing is to remember to consider that line y equals x, that reflection, and having a look at the inverse. It helps us identify exactly what that inverse function is. So quickly recapping, we've talked about what does it mean for an inverse function to exist. An inverse will always exist, but it won't always be a function, depending upon the original function. What are those conditions? The original function should be a one-to-one function. And we've had a look at a question where a function is not a one-to-one function, and we've talked about or discussed how we can work with the domain of that function to correctly identify a possible inverse. Thank you.